Hi, this is Scott and Tyler. We're going to be talking about an algorithmic approach to navigation. Say there's 2 points on a map, for example, Google Maps, point A and point B. We're going to explore the best way algorithmically to find the quickest path from point A to point B.
So the best algorithm for this problem seems to be A-star search. With A-star search, you can search on a graph or a tree. In this case, it lends itself to a graph representation because roads and highways can be represented as edges and intersections can be represented as vertices. And then when relating to the mapping problem and giving directions, distances and speed limits can be used in order to come up with edge weights. So we're going to talk about first how A-star works. So say we are in this bottom left corner and we want to find the best path to this corner or this box with the X in it using the Manhattan distance heuristic. That is, move from one cell to the next costs 1. So first what we will do is we will explore the surrounding cells, the cells surrounding our current cell, here and here. We will see that both of these cells have a cost of 1 in order to reach them, and then also a heuristic value of 1, 2, 3, and 1, 2, 3. We're just going to use up as the default motion when they're equivalent. So first we'll move up, then we'll open the new surrounding cells here and here. This one has a cost of 2 to reach it, and this one also has a cost of 2. And then they both also have heuristic values of 2. Once again, our default motion will be up, so we will move up to the next cell, opening 2 more cells. This one will have a cost of 3, and this one will have a cost of 3. And they'll both have heuristic values of 1. Once again, we'll move up as the default. Opening around this cell once again, we'll open this cell and this cell. They'll both have costs of 4 in order to reach them. But this one will have a a heuristic value of 2, being 1, 2, whereas this one will have a heuristic value of 0. So instead of going up this time, we will move to the right. We'll evaluate this position and see that it is the goal position that we desired.
A-star and similar algorithms use heuristics. A heuristic is something that helps determine the cost to a goal state. In order for a heuristic to be admissible, it can never overestimate the true cost. This is important because it guarantees optimality in a solution. 2 common heuristics are Manhattan distance and straight line distance. Manhattan distance are, for example, what we used showing A-star, where the world is split into cells, and each cell represents a node, and you can connect the nodes into a graph. Straight line distance is similar, but let's say instead of connecting the cells like this, straight line distance is just a straight line from point A to point B. A heuristic that's common in navigation is the Haversine formula, which basically, instead of going through the Earth, connects 2 points on a sphere, point A to point B. You can set U, in this case, as the North Pole, and then point A is V, and point B is W, and then C right here is the arc that represents the distance.
Finally, we're going to talk about other considerations that can be built into a mapping software. For example, what do we do if there is heavy traffic, or what do we do if there is construction that was unforeseen? And the solution to this is, instead of using an A-star search, use a D-star Lite search. D-star Lite incorporates replanning into its algorithm, that is, reusing previously found paths with updated heuristic values in order to come up with better solutions more quickly, in order to dynamically analyze the world.
Thanks for listening. Hope you learned something. Thanks, and gig 'em.